today we will be moving into the new module, that is the second module, which is about multi-degree of freedom system. So, we have talked in details about the different aspects of single degree of freedom system. We have learned several concepts of vibration using single degree of freedom system. Now, we will translate to a slightly more complex system, which is a multi-degree of freedom system. So, multi-degree of freedom system is most of the real life structures often are also multi-degree of freedom system. So, we will start with 2 degree of freedom system, with which this example we will explain different concepts of a multi-degree of freedom system, because it is easier to explain the concepts using a simpler example of 2 degree of freedom system. So, you will see that extension from 2 degree to multiple degree or multi-degree would be very straightforward. So, I will talk about 2 degree of freedom, but I will keep saying how the concepts that are being derived and explained for 2 degree of freedom system can be extended to a multi-degree of freedom system. So, let us move on to multi-degree of freedom system. So, let us go to the very classical example of a spring mass system. So, here I have a 2 degree of freedom system, which is a very simple example where I have 2 concentrated mass m1 and m2. So, I have 2 masses m1 and m2, unlike one single mass in single degree of freedom system. Here the degree, so these 2 masses are constrained to move only in the horizontal plane, and therefore, the 2 degrees of freedom that I have here is the horizontal displacement of mass m1, which is u1t, and u2t, which is the horizontal displacement of mass m2. You can easily appreciate that u1 and u2 are independent of each other, and u1 and u2 completely explains the vibration of this system of 2 masses connected with each other with 2 springs K1 and K2. So, we have 2 springs which are linear and the spring constants are K1 and K2. To start with, I will talk only about free vibration. I am not going to go into force vibration, and you might notice that I have not considered damping here. Okay. So, we will introduce damping into a multi-degree of freedom system later, but right now we have an undamped system under free vibration condition. So, the first thing that we need to do is to draw a free body diagram of the system and thereby find out the equation of motion. You will see that finding out the equation of motion of this system is very similar to the way that you did for a single degree of freedom system. So, let us first draw a free body diagram. So, let me first draw a free body diagram of this system. So, let me first take mass m1. So, this is mass m1, it is undergoing a displacement u1, therefore, it is experiencing an inertial force which is nothing but m1 into u1 doubled, and then there would be a spring force which is k1 into u1, and there would be another spring force which is going to be K2 u2 minus u1. Since I have taken u2 minus u1, I have the spring force in this direction. So, this is for the mass 1. So, similarly for mass 2, I can again draw the free body diagram, and this is also going to be very similar, and I have mass m2 which is undergoing a displacement u2, Therefore, the forces are inertial force, which is m2 u2 double dot, and then I will have k2 u2 minus u1. So, this are the two free body diagram of the system. So, if this is the free body diagram, from the balancing of forces we can find out the equation of motion of the system. So, if I try to write down the equation of motion, what I need to do is just write the by force balance, right. So, I have to write the force balance equation. So, by doing the force balance on mass m1, I can write that as m1 u1 double dot plus k1 u1 minus, because this force was taken in the negative direction. So, I have k2 u2 minus u1. So, equals to 0, since this is a free vibration problem and there is no externally applied force. So, this equation can be rearranged and written as m1 u1 double dot plus k1 plus k2 into u1, okay, and minus k2 u2 equals to 0. Let me call this as equation 1. Similarly, let me write, so this is for mass 1, I have written this for mass 1. Similarly, I can write it for mass 2 and get m2 u2 double dot plus k2 u2 minus u1, and that is equal to 0. So, this can actually be rearranged and written as m2 u2 double dot minus k2 u1 plus k2 u2, and that is equal to 0. So, let me call this as the equation 2. So, unlike single degree of freedom system where we got only one equation of motion, here we are getting two equations of motion, which are the equation 1 and equation 2. So, one equation of motion for each degree of freedom. So, if I have a multi-degree of freedom system with n number of degrees of freedom, there are going to be n equation of motion. So, if I have a MDOF system with n degrees of freedom, I will have n equations of motion. Okay. So, now let us see. So, once we get the equation of motion similar to single degree of freedom system, our next job is to solve this equation of motion. So, in previous case it was very easy to solve the equation of motion because it was only one ordinary differential equation with one variable, and we could adopt the conventional solution of such ordinary differential equation and solve it. But in this case where I have 2 degrees of freedom, it is not that straightforward, and we have to do some analysis and some more mathematical steps to solve this equations of motion. So, let us see how are we going to solve this equation of motion. So, let me just go back to this. So, let me do this. So, what I have got the equation of motion. So, let me write them in matrix form. So, writing the equation of motion in matrix form, Okay. So, if I write them in matrix form, you can see that they will look something like this: M1 0 0 M2 into U1 double dot and then U2 double dot plus K1 plus K2 minus K2 minus K2 and then K2, and that into U1 U2 is equal to 0. So, let me call this as equation 3. Okay. So, this is nothing. What I have done here is a very simple exercise. I have just taken the two equations and just written them in matrix form. So, this equation is nothing but M1 into U1 double dot plus K1 plus K2 U1 minus K2 U2, that is the equation 1, and then I have M2 into U2 double dot minus K2 U1 and plus K2 U2 equals to 0. That was my equation 2. Now, once we write the equations of motion in this matrix form, this matrix is called the mass matrix, or expressed as M, and this matrix is called the stiffness matrix, and expressed as K. So, when we have a linear system, there are certain properties of this mass matrix M and mass matrix K. The mass matrix M and the mass stiffness matrix K are symmetric in nature. So, they have to be symmetric. For a linear system, they are symmetric matrix, both the mass matrix as well as the stiffness matrix, they are symmetric. So, just to revisit the definition of symmetric matrix, K transpose is going to become K and M transpose is going to be M. Okay. There is one more property. So, this is the first property, let me call this A, that they have to be symmetric. There is a second property which is called positive definiteness. So, this matrices are positive definite. The mass matrix is positive definite, the stiffness matrix is also positive definite. What is the meaning of this term positive definite? Positive definite means that the eigenvalues of this matrix are always positive. So, if I try to find out the eigenvalues of matrix M and K, they are always going to be positive in case we are solving a linear system. What we are doing here? We are always dealing with linear system. These matrices are going to be positive definite. That is, the eigenvalues of this matrix are always greater than 0. There is a special case when the eigenvalues are equal to 0, that only happens when there is a rigid body mode. We will talk about it in detail later, what is meant by rigid body modes and what does this eigenvalues physically implies. So, these two things which actually can be derived and shown, which we might do at a later stage, should always be kept in mind, that whatever be the system, if it is a linear system, then the mass matrix and the stiffness matrix are going to be symmetric and positive definite. Sometimes they are positive semi definite, that is the eigenvalue is not greater than 0, but equal to 0, but that is only under a special case where you have a rigid body mode. Now, this is for a 2 degree of freedom system. My mass matrix is 2 cross 2 and my stiffness matrix is 2 cross 2. So, if I have a multi-degree of freedom system with n number of degrees of freedom, if I have an MDOF system with n number of degrees of freedom, then my mass matrix and stiffness matrix are going to be n cross n, which is pretty straightforward, right, pretty understood that for a 2 by 2 system where the degrees of freedom are 2, I get a mass and stiffness matrix which is 2 cross 2, which are 2 cross 2, and if I deal with an n degree of freedom system, the mass and stiffness matrix are going to be n cross n. So, the size of the matrix is always equal to the number of degrees of freedom. Even when we deal with a multi-degree of freedom system, the stiffness and mass matrix with n number of degrees of freedom, where n could be anything, could be 100, could be 5, could be 10,000, could be 1 lakh, whatever. But if it is a linear system, I mean the systems that we are talking about, it has to be a symmetric matrix as well as a positive definite matrix. Now, my next job, so we have talked about the properties of mass and stiffness matrix, what do they mean, how do I get them? Now comes the question, how are we going to solve this matrix equation 3 and get the response u1 and u2 t. So, my next job is to solve this to get u1 t and u2 t. So, that is what we are going to do next. So, let us understand. So, in order to solve the previous equation, we need to understand what is meant by normal mode of vibration. So, this is a special form of vibration which has a very important physical meaning, and we will talk about that in detail. Okay. So, let us try to understand what is normal mode of vibration. This is an essential or fundamental concept of multi-degree of freedom system, and if one understands this clearly, the physics of what is normal mode of vibration, the problem of multi-degree of freedom system becomes very straightforward. So, suppose I have a 2 degree of freedom system. So, under normal mode of vibration, I emphasize only under normal mode of vibration, which is a say a special form of vibration or a particular form of vibration. So, if I have a 2 degree of freedom system with mass m1 and m2 and the degrees of freedom are u1 and u2 at t equals to 0. So, at t equals to 0, they are at a certain position or at an equilibrium position, which is given by this figure. Now, what I do is that, let me see. So, suppose this 2 degree of freedom system is undergoing vibration, and at a time instant t equals to t1, this is going to have this is how the system is going to look like at t equals to t1. So, it has vibrated and it has deflected from its original position, and this is how it looks like at t equals to t1. So, this distance is nothing but u1 t1 and this distance is nothing but u2 t1 sorry. Okay. So, let me repeat that this figure, this light blue color figure shows the displaced position of the 2 degree of freedom system at time instant t1 and at time instant t1 at under normal mode of vibration, okay, which for time being let us assume that it is a special case of vibration. Now, let us see what happens at the next time instance. So, at the next time instance, it will again move into another new displaced position, which is shown by this green color, and this we can call this as, this entire thing we can call this as u1 t2 and u2 t2, right. Now, under this special case of normal mode of vibration, it is seen that the ratio of the displacement remain constant with time, or the deflected shape of the system or the 2 degree of freedom system in this particular case is going to remain constant. So, this is called the synchronous motion, that is, the shape of the structure undergoing vibration remains unchanged with time. How can we express this in mathematical terms? We can say that the ratio of the 2 displacement, that is u1 by u2 t1, okay, which is the ratio of the degrees of freedom u1 and u2 at t equals to 1, is equal to the ratio of the degrees of freedom at the next time instance t2 which is at t2 and so on. So, I can write this in a generic form as u1 any arbitrary t by u2 at the same arbitrary t has to be constant. That is, it cannot be a function of time, right. So, this whole form of vibration is called the synchronous motion of the 2 degrees of freedom, and this happens under normal mode of vibration. So, let me show another example. So, suppose this is another degrees of freedom where the values of m1 and m2 are different, and I have a 2 degree of freedom at t equals to 0, and so at t equals to t1 this is the deflected shape of the system. Okay. Unlike the first example, now one mass is moving in the negative x direction and the other mass is moving in the positive x direction. So, in at time instant t equals to t1, at the next time instant it is again going to get deflected further, but the shape of deflection is going to remain same. Even here I can write as u1 t1 by u2 t1 has to be equal to u1 t2 by u2 t2 is constant, and therefore, u1 at any time instance t by u2 at the same time instant t, and that should be equals to constant. Okay. So, therefore, let me summarize this, that normal mode of vibration is that typical or special form of vibration under which the masses undergo synchronous motion. So, let us see how can we explain this mathematically and how is this going to help me in solving the problem. I have seen that under normal mode of vibration, u1 t by u2 t has to be equal to constant. Since it is constant, since u1 is a function of time, u2 is a function of time, but the ratio of this two is constant, there is only a possible form of solution of u1 and u2 which is going to satisfy this condition. So, what should be u1 and u2? What should be u1 t and u2 t such that this expression is satisfied? If I can write that u1 t is some a1 into f t and u2 t is another constant a2 into f t. This f t and this f t are same, then I can see that this criteria of synchronous motion under normal mode of vibration is going to satisfy. So, this is a possible solution for this condition. Okay. So, let us assume that f t is nothing but cos omega t minus phi. I am just arbitrarily assuming this. I am just saying that let us assume f t is equal to cos omega t minus phi, and let us see whether this is going to be a possible solution for the equation that we have. Okay. So, so my u1 t now becomes a1 cos omega t minus phi and u2 t becomes a2 cos omega t minus phi. So, this is the assumed solution of u1 and u2 t, and this also satisfy the criteria of synchronous motion. Now, once we have assumed the value of u1 and u2t, my next step therefore is going to substitute this into the matrix form of equation of motion that I have got and try to solve for a1, a2, omega and phi. So, we will take that up in the next lecture. Thank you.